we've got 4 different configurations of a wire loop near a long straight wire. The current is varying, so the magnetic flux through that loop is going to change with time because the current is changing. So I'm just going to redraw the wire here down below. All right, so initially there's a current in the wire that's small. And later that current becomes larger because they said the I is increasing. Let's see how the magnetic field around the wire is going to change due to this changing current, right? So initially you would use the right-hand rule. You would just wrap your fingers around this wire with the right hand, and you would have to let your thumb point up because that's the direction of current. So it would look kind of like that. Now this tells us that the magnetic field is going into the page over here, but it's weak. Just 2 X's inside the loop. And then over here, we would of course have dots. Okay, now, as time goes on, this magnetic field is going to get stronger. Okay, so I could represent that with just a lot more dense X's here. And we can see how the magnetic field in the loop is changing because of the increased current. And there's going to, of course, be more dots over here, but that doesn't really matter to the problem. All right, so what we want to do is figure out what direction is the field and the flux, and is that flux increasing or decreasing? Those are always like the 2 questions to ask yourself. So I'll say that this is the B existing, the existing magnetic field. And then this is also the existing magnetic field because it's changing. Okay, now in my analysis, I could say that the B is directed into the page. Okay. I also see that the magnetic flux flows into the page. And not only that, but it's increasing in the direction into the page. So the law that we want to use here is called Faraday's law and Lenz's law. It basically says that there will be an induced EMF whenever there's any kind of change in the magnetic flux with time. And that is definitely happening here because the magnetic flux is defined as BA cos theta, right? So here, the thing that's changing is not the area this time, it's the B field. The B field is changing. And so an EMF will be induced in this loop, and that will cause a current to flow, according to the law. So what we'll have is we'll want to look at our picture and decide, should the induced field be directed into the page or out of the page? So those are the two options because of our loop being in the plane of the page. We can either put more X's in, or we could put dots in there. So X's is not the right choice because the flux is already increasing into the page, but Lenz's law says that the induced flux should try to stop it from changing. And so since the existing flux is increasing, we'd want to create a flux that would oppose it, so that when these two things get added together, they would cancel back to the original flux, basically. All right, so the green here is what's called B induced, the induced field. So B induced is directed out of the page. So now you just want to use the right-hand corkscrew rule for current in a loop. Okay, so just imagine grabbing that loop with your right hand, but you have to grab it so that your fingers are pointing out of the page in the center of the loop, because you want your fingers to point in the direction of the induced field. Okay, so just grab it like this. Okay, and then when you do that with the right hand, the thumb points counterclockwise. All right, so the direction of current that's induced in this loop is counterclockwise. It's called I induced. And it'll just go through the whole loop. All right, I hope that example is clear. This was case 1. Now let's try case 2. All right, so I'll go through this one a little quicker. We'll do before and after. Okay. So at the start of this, the current is small, and then it gets bigger. Right hand rule. Grab the wire like this. The thumb points to the right, but the fingers now are showing that the magnetic field would actually be directed out of the page. Okay. Afterward, though, it gets more intense out of the page. All right, so the existing B is increasing in magnitude out of the page. We have to stop that. We have to counteract it with a field that points into the page. Now, in order to find the direction of current, I just wrap my fingers around such that they're actually going to point in to the center of the loop, like that. And when you do that with the right hand, the thumb points clockwise. So the induced current will be clockwise. Now let's try a little bit tougher ones, where the field is decreasing. When the field increases, we just have to stop it with like the opposite type of flux, right? Now let's see what happens when the magnetic field is decreasing. It's a little different. Case 3. You've got your loop. You've got your wire. That's the before. And this can be the after. Decreasing current means it starts large and ends up small. We'll do the right hand rule. Thumb points up. Fingers wrap around as such. That tells us that we're going to have an existing field directed out of the page over here. But it's a strong field. It's going to get weaker over time. So let's write down that the magnetic flux that's existing is flowing out of the page. And it's decreasing. In strength. All right, so we have to stop the change. You don't always have to go against the field. You don't always have to stop the field. What you have to stop is the change. So when we draw our induced field, should it be X's? Or should it be dots? It should be dots, because you have to replace the dots that were there originally. That keeps the overall flux the same as what it was originally. So this is B induced. The red was the existing field. All right, finally, we'll do our right-hand rule. According to the right-hand rule, if the fingers come out of the center here, then the thumb points in the counterclockwise direction. So that's I induced. All right. So for the last one, Case 4. Well, we've got a current that is large at first, then it gets smaller. We would have X's in this situation, a lot of them, because of the strong current. Later, not so much. We'll want to supplement the missing X's with X's of our own. Okay, so just grab the wire, fingers point into the center of it, and the thumb points to the left. Therefore, the induced current is clockwise.